So mathematically, we want to use something called the Henderson-Hasselbach equation when we're dealing with buffers. There are other ways to solve for buffers, but this equation is pretty useful. You'll notice it's written in terms of pH. Remember, pH is the negative log of H plus. pKa, and pKa is the negative log of Ka, so that would be the Ka for the conjugate acid contained in your buffer, plus the log of the ratio of base to acid. So this works pretty well over the ranges of buffer concentrations that we are going to be doing calculations with. You notice this value, the ratio is always going to fall somewhere in there for the equations that we're going to look at, and the concentrations must exceed Ka by a factor of 100 or more, which has been true for everything we've looked at. There are very few weak acids that are so strong that they do not exceed that factor. So for what we're going to do with buffers, this equation works really well. So let's take a look at a couple of examples. So in the first example, we want to find the pH of a buffer solution that has been mixed. So according to the Henderson-Hasselbach equation, pH is equal to pKa plus the log of the concentration of the conjugate base over the conjugate acid, okay, in general. So in order to solve this equation, you need to know the Ka for the ammonium ion. The Ka for ammonium is equal to 5.6 times 10 to the negative 11th. Okay, and you'll notice that the Henderson-Hasselbach again uses pKa, which is the negative log of Ka. So pKa is equal to 9.26. So I want to know the pH, the pKa at 9.26 plus the log of, now my base is ammonia, my acid is ammonium. So ammonia 0.24, ammonium 0.20. So the pH for this would be 9.34. So that's pretty straightforward. Okay, so one of the things we want to show is that when you add a strong acid or a strong base to a buffer solution, that the pH is not going to change very much. So then that's what we're doing in part B. So when we start looking at questions like part B, I'm adding NaOH. NaOH is a strong base. So first of all, that means I'm going to have a left to right equation, because whenever I have a strong acid or a strong base reacting, the equation is left to right. So if sodium hydroxide is a strong base, and we're dealing with Bronsted-Lowry acids and bases, that means the strong base OH minus is going to react with the weak acid, which is the ammonium ion. And it's going to react completely. So I'm going to get H2O and NH3. So you'll see what happens qualitatively is that the OH minus will use up some of the ammonium. So my concentration of ammonium is going to go down a little bit. And then my concentration of ammonia is going to go up a little bit. So in this case, you'll notice I'm adding a number of moles. So that means one of the things I need to do is to figure out the number of moles of ammonia and ammonium I have, and then I need to see how they change, because right now I have a left to right reaction, and that's a stoichiometry reaction. So over here on the side, I know I'm adding 0.050 moles of NaOH to a half a liter of solution. So if the concentration of ammonia is 0.24 moles per liter, so the concentration of NH3 is equal to 0.24 moles in 1 liter, that means I have 0.12 moles in half a liter. Likewise with ammonium, the concentration of ammonium is 0.20 moles in 1 liter, which means I have 0.10 moles in 0.5 liters. So since this is a left to right reaction, and I know I have 0.005 moles of OH minus, and I have 0.10 moles of NH4 plus, left to right reaction, the first thing I need to figure out is how much ammonia am I going to produce. So right now in my buffer I have 0.12 moles. So these are the number of moles that I'm starting with. This is a left to right reaction, which means that one of these two things is going to be used up. The OH minus is going to react with the NH4 plus until one of them is totally gone. And looking at these numbers, the thing that's going to be totally consumed is the hydroxide. So that means at the end of the reaction, so over here I'm going to label this is my initial, similar to an equilibrium table but not quite. So I begin with 0.0050 moles of this and 0.1 moles of that and 0.12 moles of that. At the end, when I have run my reaction, I'm not going to have any moles of hydroxide because that's my limiting reagent. My moles of ammonium are going to be 0.10 plus, or excuse me, minus, because it's going to react with the hydroxide, minus 0.0050 moles, and that's equal to 0.095 moles. So that's how many moles of ammonium are left at the end. On the product side, I'm going to add 0.005 moles of ammonia because everything's in a 1-to-1 mole ratio. So however much ammonium I react, that's how much additional ammonia I will get. So in the end, I'll have 0.12 plus 0.0050 moles, or 0.125 moles of ammonia once this reaction is complete. All the hydroxide is gone, and now I just have ammonia and ammonium. Now, when you go to use the Henderson-Hasselbach equation, you'll notice that my conjugate base and acid are a ratio. And also remember, if I have a buffer solution, that means both solutions, both conjugate acid and conjugate base, are in the same container. So the volume is identical. So I can make this ratio a ratio of concentrations, as I did in part A, or a ratio of moles, and I will get the same answer. So in this case, the pH of this solution after I've run this reaction is going to be equal to pKa plus the log of, now I have 0.125 moles of ammonia and 0.095 moles of ammonium. And that's equal to 9.38. So you can see the pH only goes up by about 0.04 pH units, which is a very, very small amount. So the pH remains fairly constant. One more equation. What concentration of acetate do I need to make a buffer with a solution of pH 5? Now again, for this you will need a Ka for the acid, and the Ka for acetic acid is 1.8 times 10 to the negative fifth. And you might as well figure this out, because if we're doing a buffer and we have Henderson-Hasselbach, we need that pKa, and the pKa is 4.74. The negative log of 1.8 times 10 to the negative fifth is 4.74. So now when I set up this equation, pH, now that is my known value, that's equal to 5, is equal to pKa plus the log. Now I don't know what the concentration of acetate is, but I do know the concentration of acetic acid is 0.5. And then I simply have to solve for x. So let's start trying to isolate x. So I know the log of x over 0.5 is equal to, I have to subtract those two numbers, that's equal to 0.26. So now if I take the antilog of both sides, raise both sides to the 10th power, I get x over 0.500 is equal to 10 to the 0.26. 10 to the 0.26 is equal to 1.82. So that means x over 0.5 is equal to 1.82. Now, when I isolate x, by multiplying both sides by 0.5, I get x is equal to 0.910. And that would be equal to the concentration of acetate ion that I need to make this buffer.